No, I think can you hear me? Okay. Zoom meeting, can you hear me? Vaguely? Will you guys stop typing just for a second? I'm sorry, I know I told you you could talk. I have to test the Zoom microphone to see if it's reading my voice or y'all's. It's reading my voice. Okay, thank you. Carry on with the conversation. Okay, let's get started, shall we? How are you guys feeling about your quiz grades? Thumbs up, sideways, thumbs down? Few thumbs downs, but mostly sideways and up. I was really impressed with the overall class average of 87. That's actually really good. Sometimes students get so freaked out for that first quiz and they're not mentally prepared that it's a lot lower. So I'm really, I was impressed overall, but if you are the one that maybe freaked out and didn't do as well as you think you're capable of, that happens, and don't worry about it. The best thing to do with the quiz now is take it and use it as a learning tool for your exam. And I posted, oh no, I didn't post it. I scheduled an announcement to post after class today with all of my best test taking tips, like how you would study in a dream world, why I think it's really, really important to do a practice exam, how to do a practice exam. And then also, like, once you get into the exam, what things you can do to help you improve your grade. So I made them in preparation for like some exams last semester, but everything I say is still the same, except like it's a week before your final. It's not a week before your final, it's 4 days before your first exam, but otherwise it applies. So if you have any questions about that, or if you want me to give you any clarification after you watch those videos, please feel free to reach out. But that's all my best test taking tips that I possibly have for you. Okay, so I'll pass out your quiz for you during recitation. I brought my Rocket book today, so I didn't have to remember to have any extra papers. Before we get started on chapter 3, what did we learn yesterday about chapter 2? Only what we learned yesterday. Don't do chapter 1.5 that we did at the beginning. Yeah, shout it out. We learned about intermolecular forces. And what are intermolecular forces? Just define them for me. Anyone, not specifically you. Interactions between molecules. How's that different from bonds? They're not as strong. Bonds hold molecules actually together. Like if we have water, these hold those atoms together and they move and function and react as a unit. Intermolecular forces are just molecules hanging out near each other. Okay. And what are the different types of intermolecular forces? Can you describe those for me? They're the weakest kind. And what are they like? Like, how do they work? You don't, I'm not only putting you on the spot. Anyone can respond. The larger the surface area, there's one other thing that kind of helps the force be. Do you remember what it is? That's how they work. So you answered the first question. He answered a question of, you answered what? He answered how much. Okay, so they work by induced dipole. I like into a bridesmaids party while you're near each other. You're like, we are near each other. We're a group. We hang out together. And then as soon as the wedding's over, you're like, bye, see you when she has a baby. And that's it, right? So that was my analogy. So dispersion forces, if it's two nonpolar molecules, like two methane molecules, if they come near each other, instead of having normally their electrons would be all evenly shared all the way around, and it would make that beautiful tetrahedral shape, right? But when they're near each other, so you'd have negative, positive, negative, positive, negative, positive for an overall kind of neutral. It's not really actually positives, they're just going to like the absence of negative, but they'll all be moving around happily to make an overall neutral molecule. But then when they come near each other, they don't want negatives hanging out near each other. So one side will go fully positive, the other side will go fully negative, making this side positive, making this side negative. And so just for a moment, that induced dipole keeps them close together like a wedding with a group of bridesmaids. Okay, and they're the weakest force, but how can you tell, like, if you have two molecules? You already answered part of this. What did you say? More surface area. And there's one other thing. We know more surface area, the stronger the force, partially because of geckos. They have a lot of surface area on their little feet, but also if you have a molecule that's branched, it has more surface area. The other one's kind of a weird one. Yeah? What? That's a great question. I love that. Also, if there's stuff in my teeth, there's chia seeds in here and they're the worst. And they get all up in my teeth. And normally I just drink this before I'm speaking. But today was chaos. So if there's stuff in my teeth, you don't be embarrassed. I won't be embarrassed. I probably know it's there. We'll just pretend it's not happening. Okay. Because I hate it when people have stuff in their teeth and they don't know. I'm like, all I can think about is if you know there's spinach in your teeth. I do know, but there's nothing I can do about it until this beverage is gone, and I have to drink this beverage or my blood sugar will crash. So, and I'll be grouchy, I'll get hangry. The question was, how can you, if you have two different molecules near, like that would do a London dispersion intermolecular force, and you're trying to tell which one could do stronger dispersion forces, how do you know? If one's more branched and has more surface area, that will be able to have a stronger London dispersion force. And there's one other thing. I think you might be communicating what I'm thinking, which is called polarizability. So if there's like a larger space around your main atom, you can more easily manipulate the electrons to go to one side or the other, and that's called polarizability. So if you have a larger molecule like iodine, those electrons are farther from the positive center, so they can kind of move the electrons more easily. It's more polarizable. You learned that a long time ago in Gen Chem 1, probably. But that's the other thing. More surface area, stronger, more polarizable, stronger dispersion forces. And that makes sense, right? Because if you can barely move this cloud around, it's going to be hard to get the negatives near each other. But if it's really easy to move the electrons to one side or the other, it's going to be really easy to get this cloud so they can come together and one be negative and one be positive. There's not going to be a lot of questions about that in this way, but it might be like, here's a plain alkane chain and here's a branched one with the same number of carbons and hydrogens, which one would have the higher boiling point? So if you had a plain one and a branched one, and they asked which one would have the higher boiling point, I convert that in my mind to which one has the stronger intermolecular forces, because boiling point is separating those molecules out from each other, and those molecules only hang around each other because of intermolecular forces. So I'll ask you, if you had a plain chain and a branched chain, which one has stronger intermolecular forces? Branched, because it has more surface area. So which one has a higher boiling point? branched because it has stronger intermolecular forces. So that's how those questions will come up. I don't think the polarizability one is usually used, but the branched one is sometimes used because it's like pretty easy to see a branched alkane chain. I don't mean in my exams. I know I won't ask you about a polarizability question on my exams. I more mean like MCAT or the ACS exam. Okay, what else did we learn about intermolecular forces? We've got London dispersion forces. What else? Dipole, what's that? Somebody describe that to me. I heard somebody say it over here. You can describe it if you want. What is a dipole force? Yes, when two molecules that have a dipole come together. And do molecules, what's the difference between molecules with a dipole and bonds with a dipole? You don't have to be the one that answers unless you just want to. Mm-hmm. Yes, you're doing great. Okay, so she said it's possible for the bonds to be polar, but the overall molecule not to be polar because the bonds pull in opposite directions and cancel each other out. So a dipole is a permanent dipole in the overall molecule, not the individual bonds, the overall molecule, that it's built into the structure of the molecule. It will always be partially negative in one area. It will always be partially positive in another area. And when those two come near each other, then the positive side and the negative side will hang out near each other. And that's not temporary, it's not induced, it's a permanent dipole built into the molecule. But the molecule having a dipole is different from the bonds having a dipole. And you have to be able to identify the bonds having a dipole and the molecule having a dipole. Okay, what else did we learn? Hydrogen bonding. What's hydrogen bonding? That's right. Hydrogen bonding is not bonding. What is hydrogen bonding? Yes, it's a super strong dipole. So basically the polarity difference between hydrogen, if it's bonded directly to oxygen, nitrogen, or fluorine, is so significant that that positive is very positive around the hydrogen and the negative is very negative around the nitrogen, oxygen, and fluorine. So it's stronger than most intermolecular forces, but one step below a covalent bond. One time I tweeted, but why is hydrogen bonding called hydrogen bonding? And somebody tried to give me a good answer and I was like, that's dumb. And then I just moved on. It might've been right, but I was like, it's still dumb. You missed the point. Okay. So I'm glad you guys didn't miss the point. Did we talk about anything else yesterday? We very briefly touched on IR. That's just being able to identify functional groups. I think these were kind of the main things. We talked about PK yesterday? No, you might have watched my videos. You're being a superstar and you watch videos and thought that was me lecturing you. It kind of was, but somebody over here said something. What? One more time? Oh, right. So we talked about how intermolecular forces impact boiling point, melting point, solubility, surface tension, all that stuff. So basically intermolecular forces are responsible for pretty much everything. So we also talked about that. You're right. Not just that they exist, but also what they do. Okay, great. Let's hop into chapter 3. I'm really excited about chapter 3. I completely revamped these notes and I think they're so much better and I'm really excited. So you guys know some about acids and bases from Gen Chem. What do you remember about acids and bases from Gen Chem? Yeah, do you remember what the names are or anything about the different definitions? Yep, what were you gonna say? Yes, so that it depends on the definitions, but that's right. So there's Bronsted-Lowry, which I like to call the basic boring. So I remember that it's the basic boring one that you learned about first, Bronsted-Lowry. So I'll just start with B's. And that's which one is that? The one he just said generates a proton. Yeah. So Bronsted-Lowry boring base is the one that generates a proton, and then boring, basic, Bronsted acid generates a proton, and then the base that goes with that is usually called a proton acceptor. So like OH minus would accept an H plus, and then that makes water. That's a classic definition. A better, more accurate definition that also encompasses all of Bronsted-Lowry is Lewis acids and bases. Does anyone remember what their definitions are? Yes. Lone pairs or electrons, however you want to think about it. So I always remember Lewis acid as an acceptor. That just like rolls off my tongue. Lewis acid acceptor, Lewis acid acceptor, and that's like in my brain. So Lewis acid wants electrons, it will accept electrons, and a Lewis base then must be donating electrons. So I don't really think about the definitions of the bases to keep them straight in my mind. For Bronsted-Lowry, I think Bronsted is the basic boring definition I learned first, that's H plus. Lewis acid is an acceptor, that's the one I learned later, and it's more all-encompassing, and that's how I just kind of keep them straight. Do you guys remember anything else about acids and bases? There are conjugate acids and conjugate bases. We're going to talk about that, and we're even going to talk about how to look at those and figure out which side is going to be favored as a product and which side is going to be favored as a reactant. So that's kind of fun. That's the first time you get to predict what happens in a reaction because of chemistry in this class. I will when we go through our PowerPoints. I just want to see what you guys remember. I'm forcing you to jog your memory. Okay, that's a good basic overall. This is what we learned in Gen Chem. That's about what I assume you remember from Gen Chem. So you're in a good place. A little bit more, actually. I didn't think you remembered conjugate bases and acids. So we're going to talk about how to define acids and bases, how to draw curved arrows, how to predict acidity, and then how to determine the outcome of the reaction. So acid-base reactions are always in equilibrium. And so we have to decide which side is going to be in higher concentrations or favored, or which side will be considered the product. So we'll talk about how to do all that. So acid-base reactions are actually the most common reaction in organic chemistry because a lot of times we'll get what we call a proton transfer, where an H plus moves over to hang out near some electrons, and that makes another part of that molecule more ready to react. So we learn acid-base reactions first in organic chemistry because they are the most common and you'll see them a lot. I'll give some examples of that at the end. Sometimes you only have an acid-base reaction, and sometimes you have that as the first step in a long chain of reactions. You can get either one in organic chemistry. So, and also because you already understand them, we're going to a degree, we're going to use them as an opportunity for you to practice curved arrows and understand how molecules are formed and how electrons move. So Bronsted-Lowry, to get to those acid-base reactions are focused on the transfer of protons. And that is an accurate description, but it's not the best description. I kind of think about how shampoo washes your hair, but soap is a general term to wash everything, right? So like shampoo is just hair soap. But if you just say soap, that cleans all kinds of things. You can have dish soap, you can have laundry soap, you can have shampoo, which is hair soap, you can have body soap, right? So like face soap, all these different kinds of soap exist, but shampoo is like a specific kind, or dishwasher detergent's a specific kind. So Bronsted-Lowry base is a specific type of acid-base reaction. It's just like, it still fits the other definition, but it's just really zoomed in on protons. My guess is, although I don't know, is that they just discovered this reaction first, and then they realized these principles applied to a lot of other things. That's my guess. So the acid will donate a proton. It's also sometimes called a proton generator. Sometimes it is only a proton, and it bonding to something else is considered donating the proton. And I like to think of it, the reason I call it basic is kind of like basic bitch, you know, not like basic in the chemistry term, basic in the like pumpkin spice latte term. So it's just like the most basic definition that you learn. It's the first thing that you learn, and it is just in this one little area, so it's the simplest definition, right? So I always think of Bronsted as the most basic, so that must be, it's the one about protons. That's literally how I think about it. That's how I remember it. And then the base is the substance that's going to accept that proton, or sometimes it's seen as actually scavenging the proton. Like sometimes in organic chemistry, we'll talk about like, oh, that thing stole that proton. We'll talk about it kind of both ways. So if you hear me say donate a proton or proton transfer, that means the proton's moving. But we also like to talk about electrons being the one that are initiating because they're more negative. So a lot of times we talk about them attacking or scavenging or stealing a proton. Sometimes that happens too. So here's a good example of one you've probably seen before. If you have water with HCl, the lone pairs here will take that proton. That's what I mean. So this is a proton acceptor, and this is a proton donating group. So this is the Bronsted acid, and this is the Bronsted base. So H plus acceptor, H plus donor, and then we have our conjugate acid. So conjugate acid is when the base accepts a proton, now it's become having excess proton. So now it's the thing that's more willing to give up a proton. And then your other thing now has become negatively charged, so it could steal the proton back. And because of that, actually, this arrow is not really correct. They're actually in equilibrium, where that proton can go from the water, or the proton can go from the acid to the water, and then you get this H3O plus hydronium ion that you've seen before. And then the chlorine could take it back, and the reverse reaction could happen where it goes back to water and HCl. That doesn't happen very often, and we'll talk about why. Yes.
So the arrow has
No, which arrow? The curved arrow here, the pink ones or the black ones? The pink ones always goes from the electron to the positive. So it'll always start at the base. And my analogy for that is like people with negative energy are the ones who are going to attack. People with positive energy don't come at you, period. They just live their lives. They're positive. They're not worried about you. And the negative is like what's really initiating the bond forming. So there's extra electrons here, so that's initiating a bond forming with the hydrogen. So that's the first thing, but can hydrogen have two bonds to it? No. So if the only arrow we had was this one, the hydrogen would be shared between the oxygen and the chlorine, and that doesn't really work. And the chlorine is really electronegative anyway, so it's like, I don't really care about that proton, bye, and it takes the electrons that used to be in the bond and has it all for itself, and that's why it becomes negative. So if we just stopped after the first curved arrow, freaking, I closed my visualizer like a dummy. Okay. So if we just go after the first curved arrow, I think it was. So think about how super polar this is, right? So this positive charge right here, it's not quite on the level of a, like what would be a hydrogen bond if there was intermolecular forces, but it's still a very strong dipole. It's like one step below a super dipole, I would say. I made up the term super dipole. That's not a real one. I don't want you guys to go into another class and say that like it's real. That would be embarrassing. So if you just had this step where these electrons formed a bond here, then you'd get HOH, there'd be a lone pair, and then you'd have this hydrogen. But we didn't draw anything ever happening to these electrons if we don't have another arrow. So that would mean that it would look like this. And then the hydrogen would be negatively charged, and this would be positively charged, and hydrogen can't really have an overly full octet. It can only have two things in its octet. It only has a duet. And so that would be violating the Lewis structure, so that's not possible. So that's where the second arrow comes in, where these electrons then go and hang out with the chlorine. Make sense? So we always start from the area with electron density and move where they're going to end up. That's what arrows do. Okay, that was a good question. Okay, so you talked about the total ionic reaction back in the day where you'd be like, these break up and these don't, and blah, 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 and then you'd get the net ionic reaction. Do you remember that from Gen Chem? Vaguely? Okay, well, in ochem, I already alluded to this, but we don't really give a crap about spectator ions. We are like, they're there. They indicate that this is negative and there's a positive thing hanging out in solution to help them. That's it. We do not really talk about them. So we usually, you will see me draw something more like this bottom one, and practice problems will be more like this bottom one, where it's like a negative and a positive, and there's no counter ions, but that's because they're sort of implied. Like we know you can't just throw OH minus into a solution, you have to have NaOH, and you can't just throw H3O plus into a solution, you have to have water with some kind of acid. You mix those together in water, and then your overall reaction is the water plus the hydroxide makes, or the hydronium plus the hydroxide makes 2 water molecules. So we really focus on the net reaction. So I wouldn't worry too much about spectator ions, but I want you to know if there's a spectator ion present, it's indicating that it's counterbalancing a negative charge. And so sometimes like, well, you guys aren't doing the Achieve homework, but if you are doing Achieve homework next semester with Dr. Berhe, next summer semester, or with your other instructors, they do pay a little bit more attention to the spectator ions. So sometimes they'll just be like a potassium hanging out, and students are like, what is this for? We don't have this in class, we don't have this on our practice problems. That potassium is to indicate that it's counterbalancing a negative charge. So that's your takeaway from this. Okay, so Lewis acids are electron pair acceptors. Lewis bases are electron pair donors. So Lewis acids acceptors, that's how I remember it. Lewis acids acceptors, Bronsted basic, and must be the proton one. That's like what I say to myself every single time these come up, so I can remember which one does what. So here's kind of a good example. This right here is, we already talked about, can act as a Bronsted acid, right? But it also can act as a Lewis acid. So you can see that this base is donating the electron pair here to make a bond with the hydrogen, and then this breaks. So the hydrogen accepts the lone pair, then the amine donates the lone pair. So this is the base, this is the acid. So in the last example, the water, that's considered a Bronsted base. It's also considered a Lewis base. Both of those are correct. So that's the Lewis acid, that's the Lewis base, and then we still have conjugate acid would be, this is the conjugate acid, and this is the conjugate base. Yes.
For the arrow reaction, maybe
That's a good question. So, something I don't like again about these slides, I took these animations because they're good animations from the other PowerPoint. All acid-base reactions are in equilibrium. However, you'll learn to be able to predict this later. This one very much favors the separation into the Cl- and the NH3+. So because of that, they do the main arrow pointing this one way. And they don't show that there's like a little slight arrow going back the other way. So I can draw for you, and we'll talk about it later as well. But really a better arrow would have been this equilibrium. Nope, I did that wrong. I always want to do two-headed arrows. This equilibrium arrow, right? Where there's like a little tiny one that indicates it's going back this way, and a major equilibrium arrow that's indicating that the equilibrium is favoring this side. But sometimes in organic chemistry, again, I like to say organic chemists are lazy. So they're like, well, it mostly favors that side. And they just leave it like that, which is not the most accurate, but does get the point across to people who have a deep understanding. But if you're teaching someone who doesn't know that it's in equilibrium, then it's annoying. So yet another thing that I hate about these slides. But thank you for pointing that out. I think that was helpful. Okay. So curved arrows and reactions, we've actually been talking about this a lot already because you guys have been asking, so thank you. They show the movement of electrons, they're making and breaking bonds, right? It always starts with the source of the electron pair, or it can start at a bond if that bond's going to be the one that breaks. So it'll either start at a lone pair or it'll start at a bond, and it's going to show where those two electrons that either make up the bond or that make up the lone pair are moving to. So this one is not correct because it starts with a positive charge and goes towards the negative. And I see this a lot. Students, I think, because your gen chem instructors, let's blame them, taught you to think about protons moving. So students want to show protons especially. That's like the number one thing that students will put the arrow starting at is protons. They want to show protons moving, and that, although it's like inherent in your desire, you're like, I'm going to show this proton moving because that's what acids and bases are about. It's not That's not what organic chemistry about. Organic chemistry is about electrons. So you have to fight that urge that your Gen Chem professors put inside your charts to start with a proton. So it points to the atom receiving the pair or where the bond is going to be formed. Positive vibes don't attack. Atoms will never be shown moving. So that proton will never be shown moving. You will only show the electrons moving. I think that's the other thing is we're used to saying like, oh, this person's going to move from here to here, but you're not talking about the main entity. You're talking about only the valence electrons. You're only talking about what's on the outside. And I think that can be hard for students. So it's like, I want to show where the atoms going to end up. And I want you to show me where the electrons are going to end up. So try to think of it in terms of that. And never violate the octet rule. So a lot of like resonance questions early on will have, if it's multiple choice, they'll have at least a few trick answers where a bond moves somewhere that there are already an appropriate number of implied hydrogens, and that's breaking the octet rule. So if you can just notice that it's not a valid Lewis structure with those implied hydrogens, you can eliminate those answers. So when you're looking at the movement of electrons, even if you're freaked out and you're not like 100% sure on where the electrons are going to move, just say, wait, how many implied hydrogens are on here? If it's going to make 5 bonds to carbon for a new bond to be formed there, don't go there. And that kind of is a simple way for you to eliminate answers on a multiple choice question just by knowing the octet rule and that implied hydrogens exist. Okay, so I want you to look at question 1 and 2 on your own. You can talk to the people around you. I'm going to give you just like 2 minutes to do it, and I want you to pick, is the left one right or is the right one right for answer 1, and then do the same thing for answer 2. Which one shows the correct flow of electrons? And break. You can talk to each other. I don't want to just be quiet. No, you're right. Okay, so which one's right for number 1? One on the left or the one on the right? The one on the left. Why? It doesn't go from the high electron density area. It's pointing from a partial positive to a lone pair. That doesn't work. What about number 2? The one on the left or the one on the right? The one on the right is correct. It's showing that a bond is forming from the lone pair to the hydrogen, and then the bond between the hydrogen and oxygen is breaking. So if you want a little bit of extra practice, you can predict the product of these reactions, and you can check with me and see what's right, but we're not going to do that right now. Okay, so bonds don't just break willy-nilly very often. There usually needs to be some kind of a driving force that makes bonds break. So usually a driving force would be something attacking. So a good example of that is in this one, this oxygen attacked here, and now this other bond has to break, right? So this bond broke because a new bond is forming. We call that sometimes an attacking group. In other instances, if there's a very polarized bond, like if you have hydrogen with fluorine, not really hydrogen, but maybe carbon bonded to a fluorine, that's a pretty polar bond. And the carbon is pretty stable on its own, especially if it's a long chain. And so sometimes the fluorine, because it's so polarized, will depart and something else will come back in bond. Those are pretty much the only two times bonds break. If something attacks and forces it to, or if a very highly polarized bond recognizes that there's something else that it can go bond to, or if it's really stabilized in a solution. Those are the only times you'll see bonds breaking. But they can sometimes leave behind a carbocation. So this is what I'm talking about, where it's a really strong leaving group. If this was a fluorine, for example, it's fine being off by itself, especially if it's in a really polar solution, because it can have water molecules or whatever all around it. So sometimes a very, very polar molecule is so negatively charged on one atom anyway, that will just depart and go off by itself, leaving behind a carbocation. And then sometimes something will steal it and leave the lone pair behind. So usually that would be like if this was a hydrogen atom and something came and stole the hydrogen atom, this bond will break and leave a lone pair on the carbon. Yes. The bonds move to the thing that they're right next to. So they won't jump around in the atom usually unless there's resonance. But we'll talk about, you're like kind of ahead of the curve. We'll talk about something called the inductive effect, where electronegative atoms can help stabilize a lone pair that's left behind.
So like if the bonds are like the example, like you know the ABL attached at the bond.
Yes.
So use the most electronegative.
Yes. Yeah, well, usually that's because there's a strong polar thing. So your negative attacking group is going to go to the positive side and kick out the negative side, kind of, because it already has most of the electron density anyway. So it's like, fine, I'll just take the rest of these electrons. Like that's how you can think of it like that. Maybe it's like if there's a couple and like a new guy comes in and tries to date this girl and their relationship is already kind of broken anyway, the original guy's like, fine, I'm just going to take my stuff and leave, right? A new bond is formed, an old bond breaks. Yes.
Is that kind of what you're talking about in the practice pattern side? The right one where the hydrogen effect, and then now you have the
Yep. So the hydrogen gets attacked and stolen. Like this is an old relationship. Somebody comes and steals this proton. So then this oxygen is like, I didn't need her anyway, and leaves. Takes its electrons and goes. Yeah, that's the exact same situation. That was a good recognition of patterns there. Okay, so we're going to talk about newish terms. So when a carbon has a negative charge on it, like you saw in the last one, that's called a carbanion. I think I've mentioned that name to you before. When it has a positive charge, so if it's lacking electrons, it's called a carbocation. This is a new term. Something that has extra electrons and can attack and form new bonds is called a nucleophile. And it's called a nucleophile because it has extra electrons, so it's looking for a nucleus to give those electrons away to. So it attacks and forms bonds with an electrophile. An electrophile is something that doesn't have electrons, and so it's going to accept and form bonds with a nucleophile. Okay, so that's kind of a lot of words, so I'm actually just going to give you this chart because I think it will help you. Lewis acids accept electrons. They're lacking electrons. Electrophiles also accept electrons. They're lacking electrons. They specifically accept electrons to bond with a nucleophile. That's their definition. A Lewis acid can also be an electrophile. When a Lewis acid accepts an electron pair to form a bond, it's acting as an electrophile. A carbocation is when that thing is specifically carbon. So these all kind of build on each other. A Lewis acid is anything that accepts electrons. An electrophile is especially when it's accepting electrons to form a bond. And a carbocation is when that thing is positive carbon. That's it. Same thing on the other side. A Lewis base donates electrons. Electrophiles donate electrons specifically to form a bond. So often a Lewis base is also an electrophile. And if it's a carbon that's donating the electrons, that's called a carbanion. That's extra electrons around it. So all these are very, very similar and they're used interchangeably a lot of times. There's very light differences between them that I've highlighted here. Like the difference between a Lewis acid and electrophile is just that one is specifically forming bonds in a reaction. The other one's like a more general term. And then a carbocation is when the thing that's acting is a carbon that's positively charged, or a carbon that's negatively charged, carbanion. Does that kind of make sense? It's just new vocab terms, basically. Yes.
The carbocation always an electrophile.
Yes, because a carbocation, well, always when it's in a reaction to make a new bond, it's an electrophile.
I guess where is always the rectangle for electrophile.
Right. Yes. So a carbocation is always a Lewis acid because it could always accept electrons, but it's only considered an electrophile in a reaction, right? I'll be like, oh, this thing's going to attack the electrophile. That's when it's in a reaction is when we use the phrase electrophile and nucleophile. I think it's annoying that we have all these different names, but it does kind of help you build like a scaffold of first you know what acid bases are, then you know what Lewis acid bases are, and now we're going to talk about electrophile and nucleophile. And those are not just in acid-base reactions, they're like kind of broader terms, but so much of organic chemistry is about the movement of electrons that Lewis acids and Lewis bases are most of what we work with, but we just switched to calling them electrophiles and nucleophiles later on. Yeah.
Is that the first row and say compost state?
Yes. What? Hang on. Yes, that's supposed to say nucleophile donates electrons to bond with an electrophile. Thank you for clarifying. If one of y'all will email me, I'll change that and update it in the PowerPoint. Yeah, and a nucleophile donates electrons to bond with an electrophile, sorry. And that definition is correct right here. Sorry, ADHD props. Okay. So here's an example, a Lewis acid. This is a Lewis acid. It's an electrophile. Oh, I have like a cute circle, but you can't even see it. What the heck? Okay, this is a Lewis acid. It's also an electrophile. It's also a carbocation because it's going to accept this electron pair to make a new bond, right? So this is all three of those. And this is a Lewis base because it's an electron pair donator. It's a nucleophile because it's attacking to make a bond. And it's a carbanion because it happens to be a negatively charged carbon. Okay. Now for your classic H plus OH minus, I want you to draw the curved arrows. I want you to predict the product, label the nucleophile, the electrophile, if that's appropriate, the Lewis acid, Lewis base, if that's appropriate, and the carbocation and the carbanion, if that's appropriate. I just like figure out which one of these definitions this category falls into.
We didn't talk to each other. This is a group collaborative, if you will.
just to keep us on track with time, I'm gonna give you about a minute more, so you can talk to your peers about it. I'm starting to hear a few more murmurs, so I'm gonna wrap us up. Okay, where did the curved arrow start? From the electrons, from the oxygen, all that's correct. Did you notice that there are two lone pairs not drawn in on this oxygen? Good, I want you to start trying to recognize that. This negative formal charge means that there's not only two lone pairs there, there's there's not only two electrons there, there's 6 electrons there, right? I'm gonna draw, oh wait, I don't think I have to draw, I think I have. The answer's on here, okay. So they start at the oxygen, oh wait, I don't wanna give you that one. They start at the oxygen, go towards the hydrogen. So what's the product? Water. What's the nucleophile? The OH minus, you can call that a hydroxide ion, or OH minus is actually what I usually call it. What's the electrophile? What's the loose acid? H plus. What's the loose base? OH minus. Is there a carbocation? No, because there's no carbons. Okay, gotcha. So this had like a nice circle that was like highlighting what went with what, but unfortunately it didn't work out. Okay, so in Gen Chem, we talk about strong acids in these very black and white terms. Strong acids dissociate 100%, weak acids don't. What you're gonna learn about as you get deeper into chemistry is we go from black and white into gray. And so actually, organic chemists don't think of strong acids on this black and white scale, or black and white thing. We think of them on a spectrum or on a scale. So there's stronger acids and weaker acids, and we kind of look on the scale of this one dissociates really highly and this one barely dissociates at all. So barely dissociates all, very weak acid, dissociates a lot, very strong acid. We don't just like label strong and weak. So I want you to kind of erase that black and white, or I guess you can keep the black and white, but then put a gradient in the middle. So go from white to gray to black, right? It's a gradient. That's most things in chemistry. As you go deeper, it's like, well, this is usually true, but there is a little bit of gray area around it. So some people think that scientific thinking is really black and white, but that's a very basic scientific thinking. The deeper you get into science, the more gray you'll find. Okay, so ochem has acidity on a scale. This is called a carboxylic acid. It does not dissociate 100%. So if we're in Gen Chem, that would be called a weak acid. It actually, in the right conditions, it will only about 1% of the way dissociate. So that would be like really weak compared to 100% dissociation. But it's really strong compared to a hydrocarbon that barely dissociates at all, right? That would be like 0.000000001% dissociation. Okay, so there's a little bit of the equilibrium arrow pointing this way because it does dissociate. But overall, this reaction would actually favor the left side, not the right side. These would be the products and these would be the reactants more, right? But it's still considered an acid because it is still willing to disassociate to a degree in organic chemistry. And so the way that we think of this in like, oh, well, I forgot about this. Yeah. Okay, so the way that we think about this in organic chemistry is we actually apply numbers to it, which is kind of weird because we don't usually apply numbers to things, but this is the case where we apply numbers, and this is something that when we get to the actual numbers, I do want you to memorize some numbers. You don't have to do math, but you have to memorize numbers. So this is a basic acid-base reaction. And if you remember, Ka is an equilibrium constant. So to calculate the equilibrium constant, you do the concentration of hydronium or H plus ions and the concentration of A minus, or the conjugate acid base, the conjugate base, I mean. This thing, the two reactants, you put that over the starting material. Basically, that sees what percent does this dissociate to. And then you take the inverse log of that number to get the pKa. So if you have a larger Ka, or if you have a higher dissociation, if you have more H+, then you will actually get a smaller pKa because it's the inverse log, which is weird. If you have a small pKa, that makes you a stronger acid. If you have a larger pKa, that means that this number is smaller, and that's a weaker acid. So small pKa, strong acid, large pKa, weak acid. So we're increasing our acid strength. A very strong acid would have like a negative pKa, -7. It dissociates highly, almost 100%, if not 100%. A weaker acid would have a pKa of 4. The weakest acid could have a pKa of like 50 or 55 or 60. So there's like, that's the full spectrum that we're using. So these are all acids, but they're weaker and stronger. And then when we look at our conjugate base, a stronger acid makes a weaker conjugate base, because a strong acid is willing to give up that proton, which means if it's willing to give up the proton, once the proton leaves, what's left behind is stabilized. And that's how I think about acids, actually, probably because I'm an organic chemist, I guess. I never thought about that before. I've always thought this was weird, but I guess not. I don't think of acids in terms of the proton. I think of acids in terms of how well can the conjugate base handle the electrons that are left behind. So can whatever is left deal with the lone pairs that get left behind when a proton leaves? So like in this case, we see OH- a lot. And that's because OH-, it can kind of deal with these being left behind. So that's why this is considered a strong acid if H+ leaves, right? So that's kind of what I think of it as. I think I have, this is the pKa scale, but I want to draw this out for you. And we'll talk about this more as we go through, but something that is somewhat acidic, this isn't a great acid, but if it's somewhat acidic, it will lose its proton to a base. So I'm just going to put like a generic base. It'll take this proton and that bond will break and you end up with an O-. And we see O- some, right, in organic chemistry. So to me, this alcohol is relatively acidic. You also know that alcohol is relatively acidic if you stomach or struggle with heartburn. Because if you drink alcohol, there's a higher concentration of protons in your stomach and it burns sometimes. Some people's equilibriums in their stomach are better than others, not mine. Okay, so, but if you have something like, we'll say, if you have this carbon molecule and it loses a proton, which is very rare for that to happen. Carbons don't like to have lone pairs on them, right? We don't see that very often. Carbanions are not happy. They want to react, right? So this is a better acid because the conjugate base is somewhat stable. And this is a worse acid. It's less willing to give up a proton because the conjugate base is not very stable. It's not happy. So if I'm trying to figure out what's more or less acidic, I'm thinking of it in terms of once that proton goes, what's the aftermath going to look like for that molecule? Can the molecule handle the damage of these two lone pairs being left behind, or is it going to totally break down? I don't know, probably because I've been listening to Dr. Kirk Honda, who does Psychology in Seattle podcast. I'm thinking about all this in terms of relationships, but like if you're willing to let your partner leave because you are a pretty stable person and you can handle life without them, that is someone that's willing to go through a divorce. If you're like, I really don't want you to leave and my life is going to fall apart, there you go. So the proton's the partner leaving, the negative charge is the aftermath of a divorce. There you go. I'm very into relationship analogies today. I don't know why. I've been listening to Dr. Honda because I was so confused after the Amber Heard trial. I was like, how can we have experts testifying the opposite? I need a third opinion. So he talks about relationships a lot, so that's probably where I'm at. I don't like this. I want experts to agree on things. Okay. So we have this pKa chart. This is not all of the pKa's in the world. Actually, what this does is give pKa's by the simplest version of that functional group. So you can roughly assign, usually things that have a bromine on them or HBr, HCl, they're gonna act like this. Usually carboxylic acids are gonna act like that. That's kind of how you use this chart. I posted a video going through that. Is one of the ones I suggested you watch before class. In the first 7 minutes, I talk about that, and then in the second 7 minutes, like the last half, I actually use pKa charts to solve problems. I recommend you watch that before you start your chapter 3 homework, so you kind of understand like how to use this chart. For your exam on Monday, I'm going to give you this chart. After that, you won't have a pKa chart on anything. But I don't want you to worry as much about memorizing this weekend. I want you to worry about figuring out how to use a pKa chart first. Okay, so that's kind of the basic idea of pKa's. Smaller pKa's are more acidic. Larger pKa's are less acidic. Now, a weakness that I have is I learned based on this exact scale what pKa's are. So sometimes people say higher pKa, and I think like higher on the list, and then I get it wrong. So a test technique that you'll hear me talk about is I know that's something that I do consistently. I'll probably do it in this class. I'll say higher pKa, more basic or more acidic. And y'all be like, what? Higher pKa is more basic. And I'll be like, oh wait, yeah, you're right. I mixed it up in my brain. Okay, that will happen. So because I know I do that, when I get into exams, I write down larger pKa equals higher pKa equals more basic. And then anytime I have a pKa question, I will mark out if it says higher or lower, because those are the words that I get wrong every time. And I write larger number, smaller number, because that makes more sense to me than higher or lower, because I learned high and low on this chart instead of high and low in terms of the numerical values. So because that confuses me, I know that that's something I consistently get wrong, and learned that based on my practice problems. And now anytime I'm doing a word problem, you'll probably even see me do it in my videos. Anytime I'm doing a word problem that asks about that, I'll usually write out like lower pKa or higher pKa number, not lower, higher. You know what I mean? Yeah. Probably on like some deep level in the idea that oxidation and reduction is movement of electrons and everyth's related, but on a bigger picture where we're at now, no. So don't worry about that. Oxidation reduction in organic chemistry also presents kind of differently than it did for you in Gen Chem. Okay, so also I want to push through until we get to recitation time, and then we'll take a break because we're pretty close. Okay, so again, we talked about how acid-base reactions are in equilibrium. And you have to be able to figure out which side will be the product and which side will be the reactant. And you know, in general, nature likes to be more stable, so the equilibrium will favor the more stable side. So the side that has more stable molecules, that's going to be the favored side, and that will be the product side. So if it's more stable, that's less reactive, that's less acidic, that's a larger pKa. Yeah, so they favor the weaker acid and the weaker base. That's the side that's favored in acid-base reactions, because weaker acids and weaker bases are the less likely to react. They're happy on their own. They don't want to give up their proton. They don't want to take anybody else's proton. They're happy, they're living their life. So that's the side that will be favored in acid-base equilibrium reactions. So here's a good example. If you have this carboxylic acid in an OH minus, the OH minus could steal that proton and leave behind its electrons on the oxygen. This is the same example we saw before. And they have this arrow, although it would be better if it was an equilibrium arrow. And so then you have the O minus in water as the products. So what I do to try to tell which side of the reaction is favored is I identify my acid and my conjugate acid. So my acid is whatever is giving up the proton, right? Whatever is accepting the electrons. My conjugate acid is whatever has accepted the proton, whatever made the bond. So it used to be the base and it becomes a conjugate acid. And then I only write the pKa of the acid and the conjugate acid. And whichever side is the weaker acid, that's the side that's favored. So the reason they didn't do an equilibrium arrow is because this side is significantly favored. There is still some equilibrium going on, but it'd be that tiny reverse arrow that I showed you earlier. So if you are not sure, in this one you probably could tell because you're like, oh yeah, water's stable, water likes to form. I could have guessed that, but you're not going to be able to tell if it's like in carbon-carbon triple bond and the acid. You'll be like, I don't know, I've never seen those before in my life. I don't know what's stable or not. This is how you tell. Identify the acid, the conjugate acid, and compare. One of my students has this thing, and I talk about this in the video too. I always get it wrong, so I'm gonna make sure I'm right. It says high to low, it won't go. I always get it wrong because of the same problem I was just talking about. So high or large pKa to low or small pKa doesn't work because the other side is favored. And then it says low to high, it will fly. So this is the smaller and it goes to the larger, so that works. So you can see that I have not memorized low and high. I've memorized the bigger number, smaller number. So that one is hard. It's hard. That one's hard for me. So, but other students love it. So low to high, it will fly, meaning if it goes from a smaller pKa to a larger pKa, it favors that side. But if it's high to low, it won't go, and the reverse reaction is favored. And I also talk about that in my video to help y'all. I think I also get it wrong in my video to help y'all because I do that same thing all the time. So going from a low pKa to a high pKa is favorable, so these are the products. If this reaction was drawn the other way, then the other side would be the product. So it doesn't matter if they're on the left or right side of the arrow, you have to figure out which side is actually going to be the product side. Okay, so practice problem break. Let's do, let's not, so that we can finish this and you have more time in your groups. I want you to have more time in your groups because we had short time before. So if there are two possible acids present, or if you're just not sure which one is going to be more acidic, you need to be able to tell which one is the stronger acid, so you know which one's going to react. It's more reactive, it's going to be the acid in the reaction. So you can look at the pKa chart, and if your pKa of your functional group is, you can sometimes roughly approximate it. So like if I have any alcohol, I can look on my pKa chart, and the pKa chart says the basic alcohol is around 16. So I'll say, oh, this is probably 16 to 18 range. Or if I have any amine with like any R groups on it, I can look at the basic amine pKa, and it's 38 if you just have a nitrogen with 3 hydrogens. So probably if you substitute those hydrogens out for R groups, it's going to be still close to 38, maybe 40. So I just kind of like will estimate based on the pKa chart, and that's what pKa charts are really good for. Sometimes that doesn't work because you're comparing two of the same functional group. So if you have two carboxylic acids that have different R groups on them, you're going to have to use your problem-solving skills to figure out which one of those is a better acid when they're both the same basic functional group. So in that case, you want to look at that lone pair left behind and use what you know about electrons and how electrons move to figure it out. So you're going to look at resonance, inductive effect, and then a little bit of periodic trends, but that doesn't really come up as much. That's why I say it's less significant. It more explains why than helps you figure out a problem. Okay, so let's start with resonance. I'm going to actually go to the visualizer because that's not the visualizer. I think it will help. So if you have a carboxylic acid that's lost its proton, it'll look like this. And if you have an alcohol that's lost its proton, it will look like this. Which one of these negative charges has resonance stabilization? The left. Remember I said resonance wasn't going away? Here it rears its ugly head again. So this lone pair will move here and this will kick up. And your resonance structure looks like this. And between these two, instead of each oxygen having a fully negative charge, each oxygen has roughly a half negative charge, right? Is there any resonance here? No, so this oxygen has a full negative on it, right? So this is better at stabilizing the lone pair that's left behind with its resonance. So that's why carboxylic acid is more acidic than an alcohol. So the pKa of carboxylic acids are usually in the 4 to 5 range, and alcohols are usually in the 16 to 18 range, and that's because of resonance. Another example is phenol and alcohol. Phenol was a group on your quiz. A lot of you guys said alcohol and benzene or alcohol and aromatic ring, and I gave you credit if you did that. But you should recognize this as the phenol functional group for the future. And that's on your recitation work today too. But if these both lose their proton and you have their conjugate bases, you can look at these conjugate bases. And does this have resonance? No. If you try to move this lone pair here, there is an implied hydrogen right there that would make 5 bonds to that carbon, and you'd have to lose a hydrogen for that to work. And once you start losing hydrogens, that's a chemical reaction. That's not resonance anymore. There's no resonance here, no resonance stabilization. This does have resonance. If you move this bond here, there'll be 5 bonds to carbon, but then you can break this one and put the lone pair right there. And it'll actually go all the way around the ring. And the negative charge will be dispersed on 4 different atoms instead of just on 1. So the pKa of this hydrogen in phenol is actually like 9 to 10 usually. And the pKa of alcohols is 16 to 18. So this is much more willing to give up its proton because it's stabilized by resonance. So if you ever are not sure because you're like, these are both alcohols, how do I know which one is going to be more or less acidic? You can ask yourself, is the lone pair that's left behind stabilized by resonance? And if the answer is yes, that's the more acidic one. So, that should say, why do you think the arrows look like that? But you guys already asked that question. Good job. I don't even have to talk about equilibrium arrows because you asked me about equilibrium arrows at the beginning. So I'm really proud of you. Okay. So acetic acid, and I have a typo anyway. Acetic acid and water can react. The pK of acetic acid is about 4.75. And then the conjugate acid, the hydronium is pK is negative 1.7 of H3O plus. So if you're comparing these two, even though this looks like it's the reactants, these are actually the products on the left side. This side of the reaction is favored because the acid on this side has a smaller pK, so it's less reactive. So if you mix together, this is actually, acetic acid is actually vinegar. So if you put vinegar and water together, you're not going to get a lot of hydronium ion. You're going to favor the side with the vinegar. There's not going to really be an acid-base reaction between vinegar and water. The vinegar is already pretty happy. It'll just stay as vinegar and the water will stay as water. Yes. Lower in number. Yes, it makes it more acidic if it has more resonance structures because the resonance structures of the conjugate base stabilize that lone pair. Okay. Great understanding. Yes.
Okay, so, if the because you said that equilibrium favors the one we have equilibrium.
The weaker acid. Yep.
Does that mean that
Acetic acid is the product. That's the side that's favored.
also acetic acid actually has a new one?
You're not looking at the acetate. That's a good question. You're looking at the acid and the conjugate acid. So what's the conjugate acid on that reaction? It's the hydronium. So you compare the two acids, the acid and the conjugate acid. Don't look at the conjugate base because that gets really, really confusing. And people are like, what's the pKa of this negative thing? I don't know. That's not on the chart. Don't do that. Don't do that. Just look at the acid. So if you compare the acids and the pKa of the acid and the conjugate acid, that's where you look at the larger pKa. I see a thing on this.
Okay, so that means the hydrogen ion has, lower pKa.
It's negative 1.7. And that'll be one that you need to memorize, but not for this exam. But you'll be able to find it on the chart. Yes.
So earlier you said that the equilibrium typically favors the side that is less acidic,
Yes,
but it's
it is true. When we talk about less acidic, we're comparing the acid and the conjugate acid. So acetic acid has a pKa of 4.75. Hydronium is negative 1.7. So that -1 means it's super, super acidic. So actually the favored side is the side that the larger arrow is pointing to. The favored side is on the left. So they just drew it reverse so that you could kind of see that idea. So if I was asking you, which side of this reaction is favored, or which side would primarily be the products on a quiz or a test, and there's usually a question like that on a quiz or a test, I want you to circle the left side in this case. Okay, and that is called the conjugate base. The lone pair that's left behind is stabilized. We call that either resonance stabilization or delocalization. So when those resonance structures stabilize the lone pair, oh, the lone pair is delocalized. It's not local on one atom, it's delocalized. It's spread out around 4 atoms or whatever. And sometimes we'll say this is more acidic because of resonance stabilization. So these are terms you'll hear me use. You don't necessarily have to memorize them, but when I say these, I want you to know what I mean, and that's what I mean. And this is just sort of showing how that negative charge is spread between the two, and that's what delocalization is. This is what resonance stabilization is. It's a negative charge not being in one area. That's just showing you the movement of the electrons for the resonance structure. So carboxylic acids are stronger than alcohols because of resonance stabilization or because of delocalization of the conjugate, the lone pair on the conjugate base. Either one of those is like an appropriate way to explain that phenomenon. Okay. So if it's not on the pKa chart and it doesn't have resonance, the next thing you can look at, or if it has the same thing, resonance, the next thing you can look at is inductive effect. So here we have 2 carboxylic acids, they're the same functional group. They both have resonance stabilization. So they would both start out being roughly in the 4 range. But again, I'm going to the visualizer. One had a very electronegative atom that is, again, delocalizing the lone pair. So if you have a carboxylic acid that gets this lone pair left behind it, that's a lone pair. I don't know why I drew it as a line. It's like I'm a biochemist all of a sudden. Both of these would be exactly the same pKa. They're exactly the same molecule. They would be the same number, same amount of willing to give up the proton. They have the same stabilization of their energy. I'm actually going to draw 3 of them. So all these are exactly the same. Now, if I put 2 fluorines right here, those fluorines will pull electron density towards themselves, right? They're polar. So they will pull electron density towards themselves. So if there's extra electrons over here, they're going to take some of the burden of that electron too. So this pKa is much more acidic and closer to about 1, whereas this pKa is still in the 4 to 5 range for if the proton was still there, because you have resonance delocalization plus what's known as the inductive effect. So the inductive effect is when, oh, my blue pen's running out. The inductive effect is when those electrons get pulled away because of electronegativity differences. So if you have these 2, this one's going to be more acidic. Now, what do you think if, I'll switch to green since this pen's running out. What would you think if the fluorines were over here? Which one do you think would be more acidic? Do you think 1 would be more acidic or 3 would be more acidic? 1 would be more acidic because why? Yes. So if someone is pulling on a tug of war rope and they're really close to you, you'll feel that a lot stronger. If they're all the way at the other side of the room and then they pull, the effect on this side is going to be less significant. So I agree with that thought process. So the closer the electronegative atom is, the stronger the inductive effect is. So if I had to guess, this would maybe be like 4.5 to actually probably 3.5 to 4.5 would probably be like roughly where this is. Like it barely makes it more acidic. It is more acidic than the plain carboxylic acid, but it's less acidic than the one with the inductive effect very close by. So if you need to know which is a stronger acid and you can't tell based on the pKa chart, you look for resonance and then you look for the inductive effect. So in this case, acetic acid is 4.75, but if you put just one chlorine on it, because it's electronegative, that becomes more acidic because it's pulling electron density away. See what I mean? Ochem's all about electrons. I've talked about electrons so much today. Have you ever thought about electrons so much in your life? And then the last thing you can look at is bond strength and hybridization. I'm not going to spend very much time on this because usually you can answer questions that come on practice problems with resonance or inductive effect, and that's it. So bond strength, if the especially if it's just like one atom in a group, doesn't come up often in practice problems, but a stronger the bond, the weaker the acid. So if it's a strong bond, it doesn't want to give up its proton, so it is a weak acid. So inherent in the phrase strong bond is weaker acid. It's a strong bond, it doesn't want to give up that hydrogen. I don't think this ever comes up. I can't think of a time where my students have really needed to know this, but I like for them to know it just to think about that relationship. And then hybridization. So alkanes have a pKa of 50. They don't want to give up their hydrogens. Alkenes, do you remember what those are? Double bond. Alkenes have a pKa of 45. They also don't want to give up their protons, but they're slightly more willing than alkanes. Alkynes have a pKa of 25. They're much higher on the scale, much more acidic. Sorry, I just did it, see? I meant they're higher on the list. I hate it. It makes me so mad, and it's a connection that I will never be able to undo. It's like permanent in there. They have a much smaller pKa. They are much more acidic at 25 than a 50 pKa atom. And that is because of hybridization. So remember I drew out, you guys have the advantage of this happened like 2 days ago. For my other students, I'm like, remember 4 weeks ago when I drew this out? That's kind of the nice thing about ochem in the summer. It's crazy, but you don't have time to forget very much. So you also don't have time to study very much. So it's like two sides of the same coin. I drew out that like sp3 hybrid, sp2 hybrid, and sp hybrid, and each one got a little bit lower because with the more S character, the more stable it was. So if it's more stable, then that means it's more stable. So it's less negatively impacted by the lone pair that's left behind. That doesn't really come up again very often. You won't need to use hybridization to answer acid-base questions. It just, a lot of people are like, well, why are alkynes so much more willing to give up a proton? And this is literally why. And it also connects back to why we spent so much time laying that foundation is the shape and the hybridization and the way that electrons move inside orbitals affects absolutely everything, including acidity. So I'm just kind of connecting those dots. But you won't need to use this to solve practice problems. This is just to give you a deeper understanding of how electrons and molecules work at like a deep level. So the more S character, if it's sp, it's 50-50. It's more acidic. It's more willing to give up that proton because the bond that's left behind can stabilize the extra electron density better because it's more stable. Yes.
The bond has hydrogen. This carbon that has hybridized bond has hydrogen.
Is stronger.
Yeah, would that be less acidic?
Yeah, that's why I don't talk about these very much.
Okay.
That's only true if it's a hydrogen halogen bond. So if it's a hydrogen halogen bond or a hydrogen, like one individual thing, you can look at a trend on the periodic table. And that's what this is periodic trends. And that's why you don't have to worry about it. It just is explaining a periodic trend. I've thought a lot about just deleting this slide. It used to be the first slide that explained acidity, and I was like, that's stupid, and moved it to the bottom. So I don't want you to worry about this very much forever, really. It doesn't ever come back up. I think I would delete it. You just convinced me. Okay. So, and that's just one of those weird things in chemistry where it's like this bond has more S character, so it's more able to stabilize that lone pair. But when you're going down the periodic trend, the stronger bonds are less willing to give up because they're more tightly bound. Has to do with polarizability and how close the electron density is to that positive center. So yeah, again, less significant. You don't have to worry about it very much. So if you can't tell what is the most acidic, but also I'm very impressed you noticed that. Good job picking up on that. But also it pisses me off that that exists. So I was like, please don't ask the question, but you did. So I'm proud of you, but annoyed at these slides. Okay. So check the pKa chart and see if there's a functional group you can use to approximate what's going on. Then if you can generalize based on that, you're good, move on. If you can't, then look at the lone pair that's left behind and ask if there's any stabilizing effects on that conjugate base. Stabilizing effects will be resonance or inductive effect. You don't really have to worry about the bond strength and hybridization. Okay. Solvent effects. This is more important for, you probably won't need this when you're answering practice problems, but you probably will need this to think about how things work in biochem. So a lot of times in Gen Chem, you had atoms on a page, and you thought about how those atoms on the page interacted with each other on the page, and then you moved on. Well, that's not the whole picture. Atoms don't exist in isolation, they exist in systems. And in fact, oftentimes in acid-base reactions, they're in water or alcohol. Like when we're in our research labs, we have a flask full of liquid that we add things to, and that liquid facilitates those things moving around and interacting. The solvent interacts with the molecules, the reactants, because intermolecular forces. So if acids are in gas phase, they don't have those solvent effects. They are kind of in isolation. So if you lose a proton and there's just like, let's say a proton floating around up in the atmosphere, that proton would just be by itself in the atmosphere, a positive charge, and it's like desperate to find something to react with because it's positively charged and it wants electrons, right? So it's going to try to find something to react with. If you put that same proton in water, what do you think will happen? Based on intermolecular forces and what you know about water, what would happen if a water molecule came near a proton? It would be attracted to the oxygen. So if you have a proton in water, all these oxygens are going to be hanging out near this proton. That's called solvation or solvolysis. So solvent actually helps reactions happen because it can make things less reactive or less destabilized because there's some solvent effects. So acids don't want to give up their proton if they're in the gas phase, because if they're in the gas phase and they give up their proton, then they're not stabilized by anything. So if you have like HCl, the proton leaves, maybe it goes away with a base somewhere else, and you have Cl minus floating around in the atmosphere, it's like, oh shoot, now I'm just by myself as Cl minus. What am I going to do? And it's like, there's so much space between atoms. There's a lot of empty space in the air. It's hard for that Cl minus to find something else. So it's very reactive and it's not being stabilized by anything. But if you take that same Cl minus and stick it in water, the positive parts of the water will huddle up around the Cl and help stabilize it until it can find something to form a true bond with. So that's not going to come up in terms of like, answer this practice problem, but you do need to understand that atoms act differently in different systems and that they're real, right? Like you're going to go into biochem and you're going to be thinking about how these atoms are acting in our bodies. So I want you to start thinking about how these atoms are acting in the world now in this class, because I don't think we get to do that very much in Gen Chem. So we start doing that in ochem. So if acids are in the gas phase, they're going to be weaker, because if they're not in the gas phase, if they're in a solution, those charges get stabilized after the reaction happens. So if a proton is lost in the gas phase, there's nothing to help it out. There's no solvent to solvate it. And I want you to practice visualizing those molecules in the air versus in solvent. I want you to, that's why I brought this up. I want you to know what's actually happening at the molecular level. I want you to look at the air and think about the fact that there are nitrogen and oxygen and free radical molecules all floating around us that we can't see. These aren't like theoretical, they exist. Okay. Acids and bases in water. This is really important for biochem. We don't conceptualize pKa in a water solution. It's in like, I don't remember what solution it's in, but in biochem, you'll think about pKa in terms of body systems, and usually body systems, the solvent is water. So if you have a stronger acid than hydronium, anything stronger than -1.7, and it's added to water, hydronium will form because it's -1.7, which is weaker. So the absolute strongest acid you can ever get in a water system is -1.7. So if there's a water system, you very likely will not have anything more acidic than -1.7. So I'm not a biochemist. I don't know exactly how this plays out in our body, but if the solvent is water, you're not going to have anything more acidic than -1.7. And that's something known as leveling effects. So hydronium ion is the strongest acid, and therefore the strongest base you can have is hydroxide. So if you ever add water to a strong acid, it completely dissociates, and the pKa goes from whatever that strong acid was to -1.7, right? Okay. So that, again, you may get asked about leveling effects in the MCAT or the ACS exam, but for the most part, I think this is an important idea to have for biochem and an understanding of how like acids work in everyday life rather than on your practice problems. Okay. So then I was going to have you try to figure out why this reaction wouldn't work in water, but I want you to have more time. Okay, and then again, usually organic, this is more important for biochem and also how soap works. Organic molecules with more water or with more than 3 carbons aren't soluble in water. Remember we talked about like if 0.3 grams or 3 grams don't go into 100 milliliters, then it's not considered soluble. And usually if it's 3 carbons, that's kind of the cutoff. Carboxylic acids actually, because they have this polar part, they can do some hydrogen bonding. So if they have 5 carbons, they'll go in, usually. It's a solution in water. So that's again intermolecular forces. But if you mix carboxylic acid with a base and put that in water, the carboxylic acid will go completely away. And you actually do that at some point in your ochem lab. So if I put like, I can't think of a carboxylic acid off the top of my head, but if I put a long carboxylic acid in water, it'll form oil pockets, right? Just like oil in water. And then if I dump some base in there, like if I have a little bit of sodium hydroxide, the oil pockets will just go away because it'll dissolve. It might be oily solid or solid, depending on how long this carbon chain is, but and that's how soap works. Soap has this is a soap molecule. It has a super large hydrophobic chain, and then it has a salt on the other side. Remember I talked about that micelle that looks like, oh, I thought I put a picture of it. That looks like a ball of sperm. This is the molecule. This is the negative side. This is the nonpolar side. It goes into water only because it acts as this salt. And then amines, they're basic, so they don't dissolve. But you can spray amine solution because if you add acid to an amine, it will dissolve in the water, and then you have Windex. Okay, and I'm not actually going to go over this because I want you to have more time to work in your groups. We're going to have 30 minutes almost. I'm so happy. Okay, so these are examples of acid-base reactions in organic chemistry. You can look at them and see if you could recreate the curved arrows and predict the reactions, like cover up one side and use this for practice problems if you want. And usually these proton transfers are one of the first steps in reaction, so you'll see these a lot. And then here's an example of that in a multi-step reaction where this alcohol gets protonated, and then that whole group leaves as water, and then something else bonds. You don't have to worry about that. I just wanted you to see that acid-base reactions sometimes are the first step in a long reaction, a long chain of reactions in organic chemistry. And believe it or not, by the end of this semester, you will be able to predict that reaction if I gave you those reagents. You don't believe it, but you will. Okay. And that's that. I'm going to get your recitation packets, and they're on the printer right now. And I want you guys, you can take like a 2-minute break or run to the bathroom or whatever. I'll be back with your recitation packets, and then it'll be recitation time. We got all the way through chapter 3. Also, did you notice it was slower today? That's what the rest of the course is going to be like. Chapter 1 and 2 are sprinting because you know a lot of it. But hopefully the rest of the course will be more slow paced. Here are your education packets. Do you want to get started on those? I'm gonna go grab your cups upstairs. Yeah. Oh, my Band-Aids.
I didn't study that.
Okay, here's your cup, so you can say you'll, if you need help. If it's yellow, try to answer it on your own. I think you'll be able to do it. And I'm gonna pass out quizzes. Where's Juanisa? Juanisa? Did you take your online quiz? Okay, I'll grade it and finish getting it back to you today.
I didn't know.